Right, in this video, we're going to be looking at graphs that enlighten and graphs that deceive. We'll be looking at various types of graphs, and then we're going to be looking at some graphs that can be deceptive. Okay. Starting off with some of the graphs that might enlighten things. One of them we'll look at is a scatter plot. Now, I'll just briefly discuss this because later on in this course, we are going to be talking about how to graph a scatter plot. Now, a scatter plot is another way of saying a scatter diagram. And in a scatter plot, it is a plot of paired quantitative data with a horizontal axis, and of course the horizontal axis is usually called the x-axis, and a vertical axis, and sometimes the vertical axis is called the y-axis. Okay, and I'll give you an illustration of what a scatter plot looks like. Okay, in this case here, you have points that are scattered about. That's why it's called a scatter plot. Okay, and in this case here, we're looking at waist circumference and arm circumference. So here we're looking at paired XY data. The x-axis represents the waist circumference in centimeters. The vertical axis or the y-axis represents the arm circumference in centimeters as well. Okay, so here, that paired data is plotted on that XY plane and is usually scattered in some form, and it's not always going to be a straight line. Okay. Now later on in the course we will be talking about what a scatter plot looks like. Okay. The next thing is a time series graph. Okay. What a time series graph is just a graph where data, and usually it's going to be quantitative data, has been collected over a series of time, over a period of time. And usually it will be in months or in years. So here's an illustration of a time series graph. In this case here we have the Dow Jones Industrial Average. The horizontal axis is the year from 1980 up to 2005. Okay, and then the vertical axis is your high numbers of the Dow Jones Industrial Average. You can see where this is going. Okay, so that's a time series graph. Usually it's going to be quantitative data, and it's going to be collected over a period of time. In this case, it's collected over on a yearly basis. Alright, the next type is a dot plot. And what a dot plot is, it is a graph where each data value is going to be placed as a point. It's placed as a point, or it could be a dot. That's why it's called a dot plot, along a horizontal scale. Okay, so in this particular case, Here's an illustration of what a dot plot looks like. These are the IQ scores of low-lead group. In this case here, you can see that we have dots here for each that represents each individual data values, and sometimes dots representing equal values are going to be stacked. Okay, so here you can see that there are 7 dots here for this particular data value. I'm not sure what it is, but you can see that there are 7 dots there. That means that there are 7 values that are equal to each other. Okay, now the one that we'll be doing in the examples that I will show you in this video would be a stem and leaf plot. And I'm just going to say here, this is what we call a stem plot, which is sometimes called stem and leaf plot. Okay. And this plot represents quantitative data, and that's by separating each value into 2 parts. And those 2 parts are going to be this: the stem, which is your leftmost digit, and the leaf will be the rightmost digit. Okay. And an illustration of that would be this right here, of the IQ scores of the low-lead group. You can see here the numbers on the left-hand side of this bar represent your stems, all the way from 5 to 14, and these numbers here on the right represent your leaf. So here you have the 2 lowest IQ scores, which are 50. The 5 and the 0 represent 50, and then the 5 with the 6 represent 56. And then these IQ scores are, in this case, 11 with the 1, that's 111. 11 with the 5 will be 115. 11, and then another 5, that's another 115, and then 118 for the last one. So, usually it shows that there are 2 data values for 115 anytime you see a leaf repeated twice, or 3 times, or 4 times. Right. And then next will be the bar graph. Now a bar graph, in this case, it uses bars of equal width. And that's to show frequencies. Of categories of, and I'm going to say qualitative data. And qualitative data uses categorical data, by the way. Okay. And let me give you an illustration of what a bar graph looks like. And by the way, this would be an example of a bar graph. And by the way, this is a multiple bar graph, by the way. This shows the income by gender, where the darker bar represents the male and the one that's in gray represents the female, from 1950 up to 2010. So we're looking at the median median income by gender. So this is a representation of a bar graph, or more specifically, a multiple bar graph. Okay. And then next, the next type of graph. Now, keep in mind, we won't be doing all of these, but I just want to bring up a few of these types of graphs that you might come across. One is a Pareto chart. A Pareto chart is a bar graph, and this is for categorical data. And this is where the bars are arranged in descending order. Okay. Now in this case here, here's an example of what a Pareto chart looks like. Here you can see the highest bar is the family and partner, and this chart represents what contributes most to happiness. And family and partner is the one that's the most frequent, that goes first, and then friends is second, and then leisure and work studies is next, and then music, and then sports is the least. Okay, so here the highest bar goes first, and then the second highest is next. So this is in descending order for a Pareto chart. Okay. Another type of graph that can enlighten things would be a pie chart. Now, what a pie chart is a graph depicting categorical data as slices. Okay. As slices of a circle. Okay. And in a pie chart, the size of each slice is going to be proportional to the frequency count for a particular category. So in this case here, if we look at what contributes most to happiness, we can depict that as a pie chart as well, where the biggest slice here deals with the family and partner, and then next is friends, then work studies, and then leisure, then music, and then sports, with the smallest piece of the pie. Okay? So this is just an illustration of what a pie chart looks like. Okay? Now, there is a suggestion about a pie chart. Okay? Now, if you're going to use a pie chart, now, one suggestion from a graphic expert would be to never use a pie chart because of the fact that it will take up a lot of ink. Okay? And then they also lack the appropriate scale in this situation of a pie chart. Okay. Another type of illustration of graphs will be a frequency polygon. And in fact, one of the examples that we will do in this video deals with a frequency polygon. Okay. So in a frequency polygon, we have this. It uses line segments. It is a graph. It uses line segments. Connected to points. Located directly above the class midpoint values. So that's what a frequency polygon is by definition. And here is an example of just a frequency polygon. This one deals with the IQ scores of a low-lead group. And here, the horizontal axis represents your class midpoints. The vertical axis represents your frequency. Now here you can see that the data values are in dots. We first plot the points on the graph, and then the frequency polygon. The polygon is always going to be a closed figure, so you're going to just connect the dots, okay, to form that polygon. Okay. Alright, so now let's look at some examples of doing a stem plot and a frequency polygon. Let's start with the stem plot as an example. Alright, in this case here we're to use the heights to construct a stem plot, and then answer the question, is there strong evidence suggesting that the data are not from a population having a normal distribution. Okay, so here we have a list of data. These are the heights of the eruptions in inches on the right hand side, and we're going to use that data to construct a stem and leaf plot for this particular situation. Now, by looking at this, the lowest number is 93. So the lowest stem is going to be a 9, and then the highest, by looking at this, was 150. So that stem is going to be 15. So we're going to go from 9, then 10, 11, 12, 13, 14, 15. Okay, so that's going to be the stems, because on the left hand side of the bar will be your stems. The numbers on the right will be your leaves. Okay? Now that 9 is going to represent 90, so we want to find numbers that are between 90 and 99. There's only one, and that's 93. So that 3 will go next to the 9 to represent 93. And then for the 10, that represents 100 to 109. And we want to find data values that are between 100 and 109, including 100 and 109. And I see one of them, 100 and then 109. So 100 will be represented with a 0. And then for the 109, we put a 9 next to that 10 to represent 109. And then the 11 is 110 to 119. Okay, so here we have 1, 2, 3 values that are 110, so we need 3 zeros. And then, let's see, there's a 111, and then there's also 118. 111 will be represented by a 1, 118 will be represented by an 8. So here we have 5 data values that are between 110 and 119. Now for the 12 will be the one from 120 to 129. And I see 5 data values that are from 120 to 129. Got a 120, 124, 127, 126, and another 120. So let's put these in numerical order. There are 2 120s, so we need to put 2 zeros here. There's a 124, so we need to put a 4. There's a 126 and 127. And then for 130, need values between 130 and 139. So for 130, we got 139, another 130, 133, and another 130. So we need 2 zeros for the 130, a 3 for the 133, and a 9 for the 139. And then for 140 to 149, which represents the stem of 14, we got 140 and 142. And then finally 150, there's only 1 number that's 150, so we put the 0 next to the 15. Now you do want to count up all your leaves here, because there must be 20 leaves, because you have 20 data values here. And in this case, we got 6 here, 5, that's 11, 14, 17, that's 7, I'm sorry, 12, 15, that's 20. Okay, so this is what your stem plot looks like, okay, for this particular set of data. Okay. Okay, here's another example of a stem and leaf plot. In this case, this looks like a back-to-back stem and leaf plot. This is an example of the format of a back-to-back stem plot representing the pulse rates of females and males from the given data shown below. And here you want to complete the back-to-back stem plot and then compare the results. Oh, by the way, let me go back to example E1, because I didn't answer the question. Is there strong evidence suggesting that the data are not from a population having a normal distribution? Well, take a look at this. This looks like it has a normal distribution because it starts low, and then it goes up to a couple of high data values, and then starts decreasing. Now, if you tilt this on the side, you'll see that it looks like a normal curve or normal distribution. So the answer to that question is no, that there is no strong evidence against a normal distribution. Okay. Now in this case, here we want to do a back-to-back stem and leaf plot for females and males, and these deals with the pulse rates. Now some of these have already been completed, so we just need to finish the ones for females and the ones for males. Okay? Now for females, the stems are in the middle. Your leaves are on the left and the right side. The ones on the left are for female, and the one on the right are for men. Let's see. Now let's start with the females. For 50, there are no 50s here. For 6, you see that's already completed for you. Now for 70s, we have a 70, a 79, a 75, a 76, another 75. Okay, so in this case, now the way we're going to do this on the left side, we're going to put the leaves in order from the largest to the smallest. For men, it's on the right side. We'll put it from the largest, from smallest to largest. This one's from largest to smallest. So we'll do that for the women, which is in this case for the 70s, it'll be a 9, a 6, a 5, another 5, and a 0. And then for 80s, there's an 84, another 84, an 87, an 88, 85, and 81. Okay, so I'm putting these in order from the largest leaf to the smallest. So it'll be an 8 first, then 7, then 5, 4, 4, 1. Those leaves represent numbers that are in the 80s. 88, 87, 85, 84, another 84, and then 81. Okay, for the 90s, there are no numbers in the 90s for females. For the 10, that represents 100 to 109. There's 1 that's 106, so we'll put that 6 on the left side of the 10. And then the highest is 126. So that 6 goes on the left side of the 12. Now for the men. For the 50s, you got 52 to 54 and 59. Now for 60s, to numbers that are in the 60s for males: 62, 64, 67, 66, 61, 60, 67, 60, and 65. So I'm going to list these in numerical order from the smallest to the largest. You got 260, so that's 2 zeros. A 61 is a 1. A 62, we'll put a 2 there. 64, I'm sorry, I'm missing that. And then 65. And then 66, and 2 numbers that are 67, so we put 2 sevens there. And then for the 70s, you got 71, 72, and a 78. So we have a 1, a 2, and an 8. And then for the 80s, you got 89, 86, 83, 83, 89. So we got a couple of 83s, so we'll put the 2 threes first. Then 86, so we'll put a 6. 89 would be 9, and another 9, because you got a couple of 89s. Okay? So this is what a back-to-back stem plot would look like if you were to complete this. Okay, now let's look at what a frequency polygon would look like if we were to construct one. In this case here, we have the given data representing the number of people from a town aged 25 to 64 who subscribed to a print magazine. Construct a frequency polygon applying a loose interpretation of the requirements for a normal distribution. Does the data appear to be normally distributed? And then answer why or why not. So here, this is what the data looks like. And in this case here, we want to construct a frequency polygon. So we know we need a vertical axis and a horizontal axis. Now we got 4 classes, so we know we need 4 tick marks and 4 class midpoints. Now the data is from 106, the highest is 792. So what I'm going to do is in increments of 100 on the vertical axis. The highest is 800, by the way, so this will be 100, 200, 300, 400, 500, 600, and 700. Now, we use the class midpoints on the horizontal axis here. If you recall, when you find the class midpoints, you take the lower class limit and the upper class limit, add them together, and divide by 2. So 25 plus 34 is 59. 59 divided by 2 would be 29.5. And then, now let's look at the class width. From 25 to 35, that class width is 10. So if I add 10 to this first class midpoint of 29.5, I'm going to have 39.5. That will represent the class midpoint for 35 to 44. Add 10 more, you'll get 49.5. That represents the class limit, the class midpoint for 45 to 54, and then add 10 more, you'll get 59.5. That represents the class limit from 55 to 64. Okay, so you can see how you can easily get your other class midpoints by looking at get the first class midpoint and then find out what your class width is for each one, and then add 10, and then just add that to the first one to get the others. Now let's do the frequency polygon. At 29.5, that's your class midpoint for this first class. That number is 106, so we're going to go here and a little bit past 106 and draw the point. And then for the 39.5, that's for the 35 to 44, it's number 756. So that's halfway between 700 and 800 approximately. And then 49.5, which is from 45 to 54, that's 792, that's almost 800. So it's a little bit close to 800. And then from 55 to 64, that's 134. Now, from 59 to 59.5, I'm going to add another class midpoint, which is 69.5. And I'm doing that because I want to close off this polygon because it is a closed figure. Now, here's where I draw the frequency polygon. I'm starting at the origin right here, and then I'm going to connect to this first point here, and then connect to the second point, connect to the third, and then the fourth, and then this last one. So this is an example of a frequency polygon. And does the data appear to be normally distributed? Okay. In this case, we can say that it is roughly a normal distribution because it starts off with a low point, then increases to the largest, and then starts declining. So this will be a rough example of a normal distribution for this particular graph. Okay. Now let's talk about, well, let me go ahead and bring up graphs that can be deceiving. Okay. So here's just a illustration or an example of a graph that can be deceiving, because they may contain errors and they can be technically correct but misleading, like in this one right here, the highway fuel consumption, where the vertical axis does not start at 0. In this case, it starts at 30. You can see that it may be graphed correctly, but it can either look exaggerated or it can be deceptive. Now, if you look at the one on the right-hand side, if you start at 0, you can see that it's a fair graph. It's starting at 0. Okay? Whereas, with this one on the left, that might be a little bit exaggerated. So in this case here, that can be something where the graph can be deceptive. Okay? So do be aware of those types of graphs that can be deceiving, and it can be misleading if you're not careful with your vertical axis. Okay? So that would conclude this particular video on graphs that enlighten and graphs that can be deceiving.